Hi guys, thanks for tuning in. In this video I'm going to talk about gradient vectors and contour plots. So we define the gradient of a function f to be df dx1, comma df dx2, all the way up to df dxn, where f is a function of n variables. In my last video, you might have seen me define this a little bit differently. You might have seen that I wrote that the gradient of f it's still going to be a vector of partial derivatives, but instead of using this squiggly d notation, in my previous video I was using subscript notation. So f partial x1, comma f partial x2, dot dot dot, all the way up to f partial xn. Those notations are equivalent. Either way, we have a vector of partial derivatives. Sometimes the squiggly d notation is nice. This squiggly d just means partial derivative. So this is partial derivative of f with respect to x2 right here. And another thing that you should keep in mind is through most of this video, we're going to think of our function f not as a function of n different variables, but typically as a function of two variables, because we're going to imagine that we have a surface living in three-dimensional space, and we want to get some sort of handle on the behavior of that surface. You know, so something like that, right? Living in three-dimensional space. Now, the gradient of f is interesting because it lives in one dimension lower than your surface lives in. So this surface is living in three-dimensional space, and if you look at the gradient vector, that's going to be df dx, comma df dy. Well, that's a two-dimensional vector. So it's kind of cool because we're getting information about a surface living in three-dimensional space from a vector that lives in two-dimensional space. And you'll kind of see that happen throughout this video. Anyway, what does the gradient vector do? Well, the gradient vector is designed to point in the direction of greatest initial increase on your function f. And in our case, our function f is going to be a surface. So the direction of greatest initial increase on our surface. Now this next little box here just says what I was talking about a second ago. The gradient vector always lives in one dimension lower than your function does. So if we have a function z equals f of xy, which is a surface living in three-dimensional space, that gradient vector for our function is going to live in two-dimensional space. That's kind of neat because now we could start to wrap our minds around things like a hypersurface living in four-dimensional space, because the gradient vectors of that four-dimensional hypersurface live in three-dimensional space, which is a type of space that we have good intuition for. So kind of cool. I'll show you that in a later video. But for now, why don't we go ahead and take this definition of our gradient vector and just practice with it. So let's compute the gradient of f for a function x cubed plus y cubed minus 3x minus 3y. Now, the gradient is a vector of partial derivatives, so we need to compute df dx, the partial derivative of this function with respect to x, which will be 3x squared minus 3. And we also have to compute df dy, the partial derivative of f with respect to y, which will be 3y squared minus 3. The interesting thing with both of these partial derivatives is that you have to remember that the other variable will be constant relative to the variable you're taking your partial derivative with respect to. So for example, y cubed is constant relative to x. So when we do df dx, y cubed just becomes 0. So that's why a lot of stuff fell out of both of these partial derivatives. Anyway, the gradient vector is going to be a vector of the partial derivatives. So here it is, a vector formed out of those two partial derivatives that we calculated. Now, we're not limited to three-dimensional space, so we don't have to just limit ourselves to an f of xy. You could do an example with f of xyz. Now, good luck plotting this thing, because this thing lives in four-dimensional space, but it doesn't matter because we still just have a vector of partial derivatives. So as long as we can compute df dx, df dy, and df dz, we're good to go. And each of those partial derivatives on their own, not too bad, right? The partial derivative of x with respect to x is 1, and then we have negative 2y, and then we have 3z squared, and there it is. We could do this in any number of dimensions. You can go up to n-dimensional space. If you become a data scientist someday, you'll be working with data sets that have a couple hundred columns in it. You could think of that as working in 300 dimensional space, and guess what? You can use a lot of these ideas in that 300 dimensional space. There's techniques called gradient descent from machine learning. It uses the same sort of stuff that you learn in this course, just lifted up to higher dimensions. Now I do have a theorem for you guys. Let's say you have a function of n variables. Then the candidates for local maxes and mins on that surface are going to be the places where the gradient vector is equal to the 0 vector. Or possibly where the gradient vector is undefined. We don't really see that come up as much as you guys saw that in Calc BC. So this condition, it's important, but typically we're going to end up with a function that is differentiable. And then if the function's differentiable, really what we're targeting are the places where we have a gradient vector that is equal to the 0 vector. And the intuition here is kind of imagine a little surface that has maybe a maximum on it somewhere, maybe a minimum somewhere else, and we're looking for the candidates, the places where you might have a max or a min. Well, where might you have a max or a min? Well, the places where you have a horizontal tangent plane. And the places where you have a horizontal tangent plane are the places where the gradient vector is equal to the 0 vector. So this is the same idea as what you guys saw in your Calc BC course. It's the same concept. The places where we have horizontal tangent planes are our candidates for local maxes and mins, and we have to do more testing to figure out if they are maxes or mins or not, because you could always have saddle points that are neither maxes nor mins, even though they do have a gradient vector that's equal to the 0 vector. But we'll talk about that more as we move along through this chapter. So again, remember that these are candidates, not guaranteed to actually be our extreme values. And we'll look more into that soon. All right, so here's a nice little example. I made a surface for you, just out of some cosines and some squares. So here's an equation for a surface, and I'm going to use Mathematica to find these two partial derivatives, because the equation for the surface, not so bad. The equation for the gradient vector, not so nice. Look at the bottom of the screen here. So I made the computer do the work here. I said, okay, Mathematica, compute the gradient of f. Compute df dx comma df dy for me, and the computer very kindly did so. And what I have in this plot is up here, I've got a plot of my surface, and then down here, I just tried to mesh a three-dimensional picture and a two-dimensional picture together. So on the bottom, you can kind of just see a collection of gradient vectors that you could have measured at various x, y values for your surface. And one thing that you guys want to get good at is eventually being able to kind of switch between the two pictures. Use a picture of a bunch of gradient vectors to imagine what the surface looks like, or look at a surface and use that to imagine what a bunch of gradient vectors associated to that surface would look like. And the best way to get your mind around that is to imagine that your surface is kind of like a mountain, and your gradient vector is kind of like a magical compass that no matter where you're standing on the mountain, you could take that compass out of your pocket and check where the needle is pointing, and the needle will point in the direction of greatest initial increase on that surface, the immediate direction that is the steepest uphill. And that's what these guys down here are, a bunch of compass readings at various different places you could be standing on the surface, and they're telling you where to take your next step if you want to go uphill as steeply as possible. I think that magic compass analogy really serves you well, because it helps you remember, first of all, that the gradient vector is living in two-dimensional space, because a compass needle is rotating in a two-dimensional plane there, but you're using that compass needle to give you information about what's happening on a three-dimensional surface. Not that different than when you guys use Google Maps to navigate. Your phone is a flat two-dimensional surface, but you're using the information on that Google Maps app on your phone to navigate through a three-dimensional world, very similar to what we're doing here. Now, one of the reasons that we like to plot gradient vectors, by the way, when you collect together a bunch of gradient vectors on one plot, we call it a gradient vector field. But we like to do this because we could figure out something about a three-dimensional object without doing all the hard work of producing that three-dimensional plot. So here is the gradient vector field for my same surface. And what you guys can tell, or, we could see that, starting at this center point, in any direction we go away from that center point, our compass needles are always pointing us away from that point. Well, if you see a bunch of compass needles trying to get you away from a particular point, that probably tells us that that's a minimum. So we know we have a surface with some minimum at the origin at 0, 0. And then we continue to get away from that minimum, and look at how the magnitude of these gradient vectors gets smaller and smaller and smaller as I get towards the corners. Well, what's happening there is if the magnitude of those vectors is getting smaller, that is telling us that we are getting closer and closer to a horizontal tangent plane. So the longer these gradient vectors, the steeper the increase, and the shorter these vectors, the shallower the increase. And so we're going pretty steeply away from this minimum here for a while, and then as we get to these four corners, it looks to us like the surface is starting to flatten out. And if you kind of compare it to the picture, you could see that we just read a gradient vector field to tell us information about this surface, which is kind of cool. You could see, we've got this minimum, pretty steep going away from that minimum, and then we flatten out at those four corners. And that's a skill that you guys will want to get good at, being able to take a look at a gradient vector field and read information about your surface from that gradient vector field. So again, the direction of these gradient vectors tells you the direction of greatest initial increase on the surface, and the magnitude of these vectors tells you how steep that increase will be. The shorter the vectors, the flatter the surface is there. And there I've just kind of superimposed the two pictures so you could see that we really did do the correct analysis. Now, there's another way to try to capture information about a surface living in three-dimensional space using a two-dimensional picture, and that's called a contour plot. And what a contour plot is a collection of horizontal slices of our surface, basically horizontal cross-sections that you get by intersecting a plane with your surface at various different heights. So on the right side, we have our contour plot. On the left side, we have our surface. And you could kind of imagine by looking at this, okay, if I collect up all of the intersections between this red plane and my surface, you get this picture. Now, any one of these curves in this picture is called a level curve. And what's special about one of these curves is it's a path that you could walk on your surface so that your altitude stays level. And it makes sense because how did we get this thing? We got it by intersecting our plane intersecting our surface with a horizontal plane. So this is called a level curve. And it's called a level curve because it's at a certain constant level, right? It's at a fixed z value on our surface. It's a path on our surface that has a fixed z value all the way around, hence a level curve. Because when you walk on it, if you were to walk on your surface along that curve, you would stay level that entire time, hence a level curve. Here's the same exact example again, but I changed the camera angle so you could see these cross sections. So the plane is still moving up and down and intersecting our surface, and you could see the cross section based on the outline of the intersection with the plane and the surface, and you could see how that kind of matches up. Now, this is not just a mathematical idea. You'll see contour plots in real life. So if you've ever seen, this is not so common in Illinois because here we live right around here, right? Not so much going on in this map because we live in a pretty flat part of the country. I think basically the area we live in was kind of wiped flat by the glaciers, many, many thousands or millions of years ago. And so the area we live in doesn't have a lot of changes in altitude. But if you ever, go visit the West and go to some of the national parks that they have there, if you were to go on a hike, you would probably stop into the national park office, pick up a map, and kind of figure out what hike you wanted to do. And if you wanted to go on a nice, easy hike, you would pick one of these level curves, and you would say, I'm going to walk on one of these level curves. And you could still go home and brag that you were hiking in the mountains, because technically you were in the mountains, but you weren't working that hard, because if you're walking along a level curve, your altitude, your z value, is staying the same the entire time you walk on that level curve. So that's a nice way to go out to Colorado, go on a nice hike in the mountains, but you don't really have to break too much of a sweat because you're not really changing altitude as you're walking. Now, in contrast, if you want to work really hard, what you do is you cross as many level curves as possible, because the more level curves that you cross, the more changes in altitude that you're experiencing. And so that's true mountain climbing. You want to walk perpendicular to your level curves if you want to climb the mountain, and you walk along the level curve if you want a nice leisurely hike in the mountains. So anyway, these contour plots are something that people do experience in real life. You could buy these maps, maps that look very similar to this. If you're ever out in a mountainous region and you want to know what you're signing up for on your hike before you actually go on that hike. Now, I could take a contour plot and I could take a gradient vector field and I could put them together and I could try to figure out their relationship, because they are related. Now, what you guys will notice in this picture is you see the same phenomenon I was just talking about. If you want to walk level, you are going to follow a level curve, and your z value is not going to change as you're walking along that level curve. If you want to walk uphill as steeply as possible, you cross as many level curves as you can, and that will take you uphill as steeply as possible. Well, if you're trying to figure out where to take your first step off of a level curve, if you want to walk uphill as steeply as possible, you would try to get away from that level curve as fast as possible. And how do you get away from a level curve or any curve as fast as possible? You walk perpendicular to it. So you'll see a relationship here where these gradient vectors are perpendicular to the level curve passing through their tail. And that's actually a theorem that we're going to prove in a later video, but it's a good fact to know now. And then as you watch later videos, it's once we learn the chain rule, it's pretty easy to prove. But again, the concept is the gradient points in the direction of greatest initial increase on our surface, and a level curve doesn't change doesn't have any increase at all, doesn't have any change in altitude. So if we want to go uphill as quickly as possible, we need to walk we need to walk perpendicular to that level curve. And so our theorem is the gradient is always perpendicular to the level curve passing through its tail. And I'm going to prove that in a later set of notes that I'm going to make a video for. So like I said, once we learn chain rule, pretty easy to prove. We haven't learned chain rule yet, so can't really prove it today or in this video, but pretty soon I will be able to. Now, notice that this is all happening in a two-dimensional representation. So what I'm saying here is that the gradient vector and these level curves are perpendicular to each other as long as the gradient vector, its tail is on the level curve. This is not saying that the gradient vector is perpendicular to the surface itself. So you don't want to get mixed up between this three-dimensional surface and this two-dimensional representation of what's going on our three-dimensional surface. So this is a two-dimensional theorem here. Don't mix it up with the surface itself, right? All right, guys. So I hope you enjoyed this video. Tune in for a couple more videos with related topics for this chapter.